They, after having seen the main feature of the Greater Himalayan sequence, the South Tibetan detachment, the main central truss, the HHD, we can give an overlook to the exhumation models adopted by for the exhumation of the Greater Himalayan sequence. Okay. Here in this picture, you can see four very popular model to explain the exhumation of the Great Himalayan sequence. And there are differences in the geometry of the South Tibetan detachment, the upper normal fault, and of the main central truss, the lower thrust, bounding the metamorphic core or the Greater Himalayan sequence. In the channel flow model, where deformation should be accompanied by erosion, where a channel of a molten rock move to the south and reaches the surface by the aid of localized erosion on the southern flank of the Greater Himalayan sequence. In this model, the South Tibetan detachment and the main central thrust should remain more or less parallel. In the wedge extrusion model that we saw 2 days ago, these two kind of fault should merge towards the hinterland, towards the north, so the different geometry is a little bit different. A different point of view has been proposed by Alexander Webb, 2007, proposing the wedge insertion model, and for him the grid element sequence is a wedge moving to the south and causing the movement along the South Tibetan detachment as a passive fault. Is a back thrust more or less for him, not a normal fault. And he bases this observation just on this part of the Himalayas where Tibetan rocks came into close contact with the rocks of the uh, lesser Himalayan part. So the shape of the Great Himalayan sequence is a wedge tapering to the south, not to the north as proposed in this model. Mm. Yeah, for this model. He found only Alexander Webb found a clip of the South Tibetan detachment very close to to the main central thrust. So a few hundred meters or very few kilometers. So going from the inner part of the side to the other part, the thickness of the grid sequence decreases up to, but maybe something similar in Bhutan there is because there are a clip of the Tibetan rocks very close to the main central thrust. The model represented in C is a critical taper that is a big wedge that affect not only the brittle portion of the Himalayan belt, but according to Matthew Cohn, it affects all of the thickness of the belt, including the brittle and the ductile portion. And in this way, it is indifferent to the geometry of the South Tibetan detachment and of the main central, thrust. Of course, this shape is preferred. Thirty, 40 kilometers. So it includes also the deeper part of the belt. This after Matthew Cohn 2008 published in Geological Society of American Bulletin. There are other mechanisms of exhumation proposed by people, maybe the Cell, Robinson, Bollinger, and so on. There is thrust and thrust propagation in duplexes. In this old paper, you can see that the Titan rocks, the Greater Himalayan rocks, the Lesser Himalayan rocks are put more or less at the same level. There is a thrust of the Titan rocks above the Greater Himalayan sequence. Then the thickening of the belt, development of South Tibetan detachment, and then the movement of the Greater Himalayan sequence above Lesser Himalaya, producing the main central thrust, some antiform and synform to external part. This is a nice model, but it cannot explain the deformation before the movement of the main central thrust, because with this geometry you should have the same pressure at the base of Lesser Himalayan sequence, at the base of Greater Himalayan sequence, and at the base of the Titan rocks. But instead, metamorphism is very different in this part of the belt, and the pressure higher in the Greater Himalayan sequence with respect to the Lesser Himalaya or Titan Himalaya. So this model is good. This is the reconstruction of Western Nepal with duplexes developed in the Lesser Himalayan sequence. There is Ramarg trust here, a lot of duplex here, antiformal stack in this part, a synform like this. This is Dale Dura trust. So this deformation is very good to explain geological feature after the development of the main central thrust, but not before, because before you should involve ductile deformation a lot. This model is not enough to explain all the exhumation. A similar model has been proposed by Sean Long, 2011 in Bhutan. You can see these green stuff are the Titan rocks. You can see some clip of the Titan rocks very close to the main central thrust here. So small difference, small distance here or here. So probably tapering to the south geometry of sequence is preferred in this part of the belt. Anyway, when a great element sequence has been transported by the main central thrust, most of the formation of metamorphism could be already happened in the Greater Himalayan sequence. So another critical aspect is the geochronology, the age of the formation in between the South Tibetan detachment here and the main central thrust, because most of the model require contemporaneous activity of these two bounding faults as proposed by Godin 2006, Antolin 2013. And these two faults played a major role in several models of exhumation of the GHS, such as extrusion, channel flow, wedge insertion. Okay, if we give a close look to the channel flow, we speak a little bit about this before. According to channel flow, the rocks, molten rocks below Tibet flow towards the south, and they go to the surface only by focused erosion. Uh, as we told 2 days ago, the deformation is mainly caused by the difference in pressure in between Tibetan Plateau and the external part of the belt. So they cause a migration of the fluid from north to south. As the other component is a simple shear due to the um, movement of India below Asia. So this kind of velocity field, the pressure causes a parabolic shape of velocity field. When we sum up this Poiseuille flow and Couette flow, difference in pressure and simple shear, the result is that the upper part of the channel is exhumed because the vector moved to the south, whereas the lower part underwent burial because the arrow point to the north. Okay, and in this way, as I already said. You need in India lower crust, very strong, an upper crust in the Tibet, very strong, the blue one. In this model is able to explain several things. The formation of granites, maybe in the upper part during the motion of a partial molt zone, inverted metamorphic sequence along the main central thrust, the erosion that act together with tectonics. And this model is based on several observations. For example, I took into account the velocity of the formation, the denudation front, the amount of material taken away from the rain, the monsoon, the radioactive heat source of the sediments from Indian plate coming in subduction, because there is more or less 2 microwatt for cube meter. That is very important, this heat source, because to melt this crustal rock, you need not only to reach depth of 20 kilometers, 30 kilometers, because they are not enough to melt so largely the sediments, but you need also an internal heat source for the Indian plate. And maybe this amount of heat source is overestimated, because there are later paper demonstrating that the heat source is not so high from the sediments from the Indian plate. So they take account also um, the the shape of the isogrades here and below. They compared the PT data from real rocks, the black one of temperature and of pressure and of temperature, and the green and the red dots are from the model. So there was a good coupling between natural model and model and the data from the model. So they build up different PT path for the lesser Himalaya here, for the greater Himalaya, for different part, from different rocks from different portion of the Himalayan belt. And at the end, but they forced the upper part, the yellow, lower part to be very strong. So this part could melt and move to the south by the difference of pressure and to be exhumed. In this other picture, they made the same people, Beaumont and others, made some experiment, and if you have this initial picture with no denudation, no focused erosion, the channel remain in depth and move only horizontally. By the help of efficient denudation along a strong raining and erosion in the frontal part of the belt for several million years, the velocity of the rocks is not horizontal, but start to move towards the surface, so the rocks are exhumed. With no efficient erosion, you have a lot of faults here, but the the channel remain in depth with no exhumation. So more or less, and in some way they are able also to explain the post-exhumation evolution with the formation of the gneiss dome that now occurs in the Tibetan Himalayan rocks, the North Himalayan dome. Okay, just a recall, this kind of model could explain the inverted metamorphic sequence um, along the main central thrust with a telescoping of this ograd just along the thrust or along the South Tibetan detachment, but in this way the isograd put in a normal situation. And what we observe now at the frontal part of the belt, there are rocks that were molten 20 million years ago. Now the molten rocks are below Tibet, and it was due mainly by the seismic profile made by Nelson 1998 from India to China. They found several low velocity zone, but after this experiment, this profile, some people found that these molten rocks are not expanded all over the subsurface of Tibet, but they are concentrated mainly among the rift, such as the Yadong Rift or other rift. So there is no a melt layer all over across the subsurface of Tibet. Uh, these are the main characteristics of a paleo of a channel flow and the exhumation of the paleo channel. Of course, you have the limit, the 650 degrees centigrade, the isotherm, that is a boundary of solid also to melt rocks. After above the rocks are molten and below the rocks are under solid state. So there is the frontal part of the channel is a crystal block made by solid rocks that are extruded. So you have channel flow and the extrusion of solid rocks by the action of the normal fault and thrust fault, aided by erosion. Some people proposed, such as Larson and Hadar, a Canadian geologist, proposed a modification of the channel flow, including the channel flow in the critical taper model. So they more or less adopted a model similar to Webb for the South Tibetan detachment, that is backthrust, in fact, not really a normal fault. And these rocks, this molten rock, pulled ahead and cut through the crust, uh, causing the formation of the South Tibetan detachment here and the main central thrust below, up to the exhumation of the rock. So for them, the difference in pressure is able to break the rock up to the surface. So this is a mixed model, but it is a qualitative model without quantitative evaluation. Uh, I would like to stress some feature because in the channel flow model, the incubation period that is required to increase in average crustal temperature to generate a low viscosity is between 10 and 20 million years. So you need much time to melt the rocks below Tibet from the beginning of the crystal thickening from the collision. This implies that all GHS should be molten at the time of the flow. So it needs to be all made by molten rocks. This means that you need to find migmatite everywhere, from main central thrust up to the detachment. But it is not really true because the first unit 1, is made of kyanite, garnet kyanite bearing gneisses that deformed under solid state. There are no migmatites at this level. So it's just a first problem. The production of melt, leucosome, equivalent with the channel flow, must be younger than the shortening structure in the overlay log, so the Tibetan Himalayan sequence. Another very important thing is that an active channel must be 10 to 20 kilometers thick to go ahead in an efficient way, because with lower thickness, lower time, the model cannot produce the channel flow. But as you shown before lunch, the thickness of the grid element sequence change a lot from west to east. Thickness changes to 10, 4 kilometers, maybe 13 kilometers in Bhutan. So not in every section there are the condition to produce the channel flow. The channel flow would have horizontal transport bigger than the vertical one. So it is difficult to explain the production of eclogites that needs large depth. Is a problem. This is a nice thing because in channel flow, vertical transport is allowed by localized erosion by the monsoon. Otherwise, the flow remains below the surface. So it was the first paper to stress about the importance of erosion in helping the tectonics. And the last thing is that main central thrust and South Tibetan detachment should be contemporaneous, but it is not really true all along the belt. For example, in India, in Western Nepal, they are clearly uh, developed in very different times. So we could give a look to this model. On the left, you have the model that require the South Tibetan detachment and main central thrust to be contemporaneous, channel flow, wedge extrusion, and wedge insertion. So this model could, cannot be applied all over the belt because the different timing of this normal fault and of the main central thrust along the same sections. In this model, the critical taper or in sequence shearing, the contemporaneity of these two boundary fault, the upper and lower, are not necessary, are not required. So they work without this feature. Okay, we come back a little bit to the in sequence shearing model that we examined this at the end of this morning. Um, The GHS is not a coherent tectonic unit. A coherent means that is a solid unit without a deformation inside, without discontinuities. But there are shear zone in it with top to the south and southwest and south shear, such as the HHD that I show you this morning. And another shear zone that we found within the Great Himalayan sequence is in central Nepal, the so-called Kalopani shear zone in Kaligandaki. Kalopani means black water in Nepal. Uh, and in this small village, we found that is a very high part of the Himalaya, of the Great Himalayan sequence. We found a beautiful shear zone just along the road, but also away from the road, that was active in between 41 and 30 million years under solid state condition with no melts inside. The melt migmatites occur only in the upper part of the Great Himalayan sequence. We have the high Himalayan discontinuity, HHT, active between 28, 27, 17 million years that separate the upper migmatites from the lower canite bearing gneiss. So if we make a very schematic cross-section through the Himalayan belt in the central Nepal, there is main boundary thrust, the main central thrust, the lower and upper, the HHD, the Kalopani shear zone in this position, and the South Tibetan detachment. So it is really a unit characterized by different shearing up to the south, but to different condition of pressure and different ages. This is a geological map of the Kalopani shear zone. This is more or less we are along the Kaligandaki River. This Kalopani village. If we go ahead, we reach Mustang, Upper Mustang, then China. Here you can see the trace of the South Tibetan detachment with marbles. South Tibetan detachment. Here, this guy is Lorenzo Gemignani that we left for 2 months in the mountain to map the South Tibetan detachment and the Kalopani shear zone. So we have here the unit 3, the upper part of the Greater Himalayan sequence. This is more or less the thickness of the Kalopani shear zone. Scattering orthogneisses, calcasilicate gneisses, and also mica schist. And we took two beautiful samples here in the mica schist, garnet and starolite mica schist, and in the orthogneisses here. Here the orthogneisses of the upper part of the Greater Himalayan sequence, deformed by myelonitic foliation with more or less SC structure and rotated porphyroclasts with top to the southwest sense of shear, so contractional shear zone. So it is a novelty, this one, because uh, is a contractional shear zone. Just you can see the scale here is 1 kilometer, 1 kilometer, 2 kilometers. So we are very close to the South Tibetan detachment, not so much a distance, but we expected to find some normal deformation. Instead, we found a contractional deformation, top to the south. We dated these samples, this since action of the garnet bearing starolite. You can see beautiful garnet. We found monazite, this small crystal inside the garnet, and the monazite along the main foliation. And we analyze this monazite with the same methodology. I map, chemical map, laser ablation, and ICP-MS connected. This was made in Italy, in Pavia laboratory with Antonio Langone. In this rock, you have garnet, white mica, biotite, starolite, plagioclase, ilmenite, and so on. Plus monazite, apatite, and zircon. We dated zircon and monazite from the orthogneiss here, and the zircon and monazite from the mica schist. You can see some holes from laser ablation. Then we analyze the same with another methodology with the Nela Rubato to be sure of the result, because we found very old edges, and we are a little bit surprised of this. So we applied two different methods, and we published this in 2016 Geological Society of America. In this uranium lead diagram, you can see the ages of the orthogneiss. Very nice concordant ages at 41 million years for the monazite along the main foliation. This is a sample from the mica schist. The red stuff are related to the monazite along the myelonitic foliation. This yellow along starolite, and the green inside the garnet. As you can see, the monazite inside the garnet record older ages, 48, 43.8 million years. This is related to increasing pressure and temperature of the garnet. So more or less the stage of prograde metamorphism after collision. And instead, the red edges, this one and this one, is along the foliation that are concentrated in between 41 and 30 million years. And this is a PT path of these rocks. So you have the pressure here, the temperature here, the possible path considering the composition of the white mica, so the garnet, all the constraint of the magnesium content in garnet, the calcium content, the silica content in white mica. So we are able to establish that this part of the path has been related to exhumation, and this part developed during the D2 formation, the formation of the shear zone. So this path has been constrained between 41 and 30 million years in this part. Okay. So if we put also this shear zone in the sequence model, we can see that the grid element sequence, comprised between the Tibetan rocks and lesser Himalayan rocks, is divided in three portions, three panels. The first one is comprised by the Kalopani shear zone and the future South Tibetan detachment, because at 41 million years the South Tibetan detachment was not yet active. The second panel is between the Kalopani shear zone of the HHD, Higher Himalayan discontinuity, that in this section of the belt has been named the Chomrong Trust, but it is present in the Kaligandaki. And the third panel is the one comprised by the HHD and the main central thrust. Mm. So the exhumation is different in between each of these panels, happened in different times with the same kind of mechanism, but in different times. Okay, with up to 41 million years, we had the undertrusting of the Indian crust below Tibet, so regrade metamorphism with no other things. Some ages record the deformation between 48 and 50 million years inside garnet, but no very good information about the kinematic. At maybe 41 million years, this deformation, this shear zone localized here. We don't know why. We don't know why deformation just choose this place to develop. It is an open question. Uh, and with this activation, we can do the same as the HH did this morning. And with this kinematic, this arrow, you can bring the point A is started to move in this position, increasing pressure and temperature. This part is inferred. This part has been calculated by TPT condition. At this time, the path changed, and this rock start to move upward. So underwent exhumation. Of course, it means that at that time there was erosion, some normal fault above. There should be somewhere because we have no information. There's also no information if at 41 million years the belt was already uh, uplifted and underwent exhumation, erosion. But anyway, something happened because the pressure was decreasing at this time. So, mm, oh, maybe another possibility is the ductile distributed thinning. You remember from 2 days before, I explained the mechanism by Shenlong. We saw that by simple shear and pure shear, you thin the greater Himalayan sequence, so the pressure could be lower and could explain part of the exhumation. So one of these three, erosion, normal faulting, or ductile thinning, could be active to exhume the rocks, the upper part. So the exhumation started in the uppermost part of the GHS. Then we have no more information after 30 million years. No dating, nothing in the rocks. Was cooler than so more deformation. Then deformation shifted towards the HD between the 26 and 18, 17 million years. So also the point, the rock in B in the middle panel started to be exhumed later than the upper one. So this rock start to move in this direction. At that time, we should have the intrusion of the Buraburi granite here. So means that in before 24 million years, there was an activation of the South Tibetan detachment, probably helping the exhumation of this the panel, this higher panel of the Great Himalayan sequence. Then there are younger granites at 20, 90 million years, such as the Mugu granite in western Nepal. So this stuff become exhumed this earlier, this later, and then the point C continue to be under trusted increasing pressure and temperature. Only at the activation of the main central thrust, all the rocks in A, B, and C were exhumed, but this started before, this later, and this later again. At this time, activation of the main central thrust, I put just the ASE, but it depends on the cross section of the belt. lesser Himalayan rocks become involved in the belt, underwent increase in pressure and temperature, and then they were exhumed by the main boundary thrust or Berinag thrust, some other lower thrust, diciamo, lower position with respect to the main central thrust. The problem is that after this, there is not much more metamorphic minerals to detect the PT condition. But anyway, this could be a more complete view to explain the in-sequence shearing. There are some problem because we try to find this shear zone elsewhere in the belt, such as in the Makalu region or Manaslu region. But it is a big problem because here, if you give a look to the map, you have calc-silicate gneisses, calc-silicate gneiss, mica schist, marbles. You have not a huge intrusion of granites or migmatites. So probably this part of the belt, no, I have not the picture that I'm looking for. This part of the belt preserved this older shear zone because there was not so much melting and not so much intrusion of granites in other places, such as Noops, Makalu, or some other section. There was a lot of melting, so the rocks were completely molten in the other part with intrusion. So the structure was more or less destroyed. This particular place where up to the South Tibetan detachment, we can observe this activity of this older shear zone. But anyway, the data, the data are in favor of in-sequence shearing model because we have the Kalopani, HHD, upper main central thrust, lower main central thrust. So when we gain information of the age of the shearing, it is moving to the south in sequence way. So probably it could explain the exhumation and the different timing of exhumation of different portion of the greater Himalayan sequence. Okay, this is from Ladakh. Do you know? Okay, have you some question about this just overview of the models? So, of course, models are very simple. I simplify the reality of the rocks and of the Himalayan belt a lot because probably also out of sequence thrust was efficient to work sometimes because we have some out of sequence thrust even in Western Nepal. We found these. There are also transverse faults and so on. So the way to well understand the origin is very hard, but the take-home message from this kind of work is that to work accurately in the field to detect the shear zone, the faults, to collect oriented sample, to analyze that at the macro scale, to gain information about the pressure, temperature, good methodologies for biochronology, mainly maybe the same methodology uh, to date the rocks because they use argon-argon on hornblende, on plagioclase, on white mica, zircon, monazite. Probably they gave different ages, so it is important to use the same methodology and the same minerals to gain the right information. And the two mix, of course, much more methodologies, much more information to build up some possible models or try to understand in a better way your data. You need to have a good data. The data should be very nice. reproducible. Each people go there, take the sample, take with the methodology, obtain the same results. And this is a very important point. Then you have to discuss this data with other people, other colleagues, and to try to best interpret your data, taking, of course, in account also data that are not in favor of the model of what are you thinking, because sometimes people tend to overestimate his own data and not to take into account the other data. So this is just a very, very simple model, but I think it will be a lot of time to go in to well understand the Himalayan belt because it is very big and not known in every place. For example, 10 years ago, we found this huge granite with people never found, never mapped. So maybe also along the belt we have different maps with different classification of rocks or units. So this is also a problem. But also, when people apply numerical models, should take into account the natural data. Because for my experience, when you put a number and models, you can build up what do you want, no problem. But if you put good data, you can try to build up more nice model. And of course, there are many variabilities, many factors. I remember the thesis of Andrea Piccolo was 100 pages with 130 models, and the first 30 pages were devoted to the parameters, to define the single parameters. So maybe dozen and dozen of parameters. If you change a little bit one number, change a lot the final result. So also numerical model are very nice, but they should interact with the data and with the people to try to find the better explanation. But they help because when you go in the field, you see only uh, the last picture of the movie, but you lose completely all the history. With the model, you can gain information about what happened since the beginning. So you think about several parameters, and so they are very useful. Okay. Yep. Yeah. 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 Um, Usually, the leucogranites in the Great Himalayan sequence are think to came from the molten part of the Great Himalayan sequence. The geochemical constraint about this. And this morning I showed so the Makalu granite where there are a lot of dikes that increase in volume up to the upper granite occupying the upper part of the Makalu. So also in the field, you can see really a large amount of dikes that increase, and at the end build up large volumes such as the Napsi granite, the Makalu granite, or the Buraburi granite. So because here you have the temperature enough to melt the rocks, the crustal rocks, and so the origin should be more or less in this part. Thanks. Some other curiosity? Hmm. Along the MCT, just above MCT, yes, but cross-cutting the MCT, no. I never found, unfortunately, because mm, mm. Yeah, but not yet. Okay. So you have not question? We can. Okay. So. Mm, mm, mm. Uh, okay, I think the chemical signature of this granite is crystal. I remember amount of strontium or other elements. So geochemical analysis of most these granite are from crystal origin, not mental origin. Also in the leucogranites in the North Himalayan gneiss dome are very similar to this one, leucogranites. So maybe in some uh, in some metamorphic domes, such as the Yardoi dome in southern Tibet, there are some very old granite at 45 million years that could show some mix with something from mental, I think. And they are very strange because they are undeformed. The Yala Zambo dome is still a problem. Mm, okay. So now we have to do something with vorticity, the vorticity of the flow, with some one exercise maybe, because we spoke about vorticity several times, and then we could go a little bit into depth for this topic. So we will deal with the vorticity of the flow, some methods and applications. Some application I show you before, but just a recall of what is the vorticity. The vorticity is defined also in a mathematical way, but I avoid to, to give you this boring stuff. Anyway, there is a nice paper by Paris Xipolias, 2010, published in Journal of Structural Geology that make a nice review of the vorticity methods. You can find also in the Pasquier and Trau book, but I will give you the PDF together with other references. So if you are interested, you can go into depth of the vorticity. I remember you that vorticity is just a method to estimate the amount of pure shear. You can see here the coaxial deformation, pure shear, where during deformation the short axis and the long axis remain in the same position with no rotations in in a field of deformation. And simple shear where all the line rotates in the direction of the shear. If you mix these two type of flow, you have the general shear or non-coaxial deformation characterized by both simple shear and pure shear, such as intranspression, intranstension. The end member is the simple shear where vorticity number is number one, equal to one, and the pure shear vorticity number is equal to zero. In between, the different values are comprised between 1 and 2. Mm. Okay, if we give a look to this picture, we can see pure shear, non-coaxial deformation, simple shear, and you can see also this kind of line, the thick black line that has a apophysis of the flow. This means that during pure shear, you have all the particle in the field of deformation that follow an hyperbolic path like this. is rotation to the right, rotation to the left, rotation to the left, to the right. Only along these two lines, the particle follow a straight path. There is no a curved path. And these two lines are called apophyses of the flow. During simple shear, you have only one apophysis, the horizontal one, the one parallel to the shear, and the second one vertical disappeared. In between full shear and simple shear, these high angle apophyses rotate in this direction. In destral shear, it rotates to the left, and this angle between this apophysis and this one is related to the non-coaxiality of the formation. So vorticity is equal to the cosine of this angle. Mm. So it is very important, but okay. So the apophyses of the flow are very important for this one. You can see here the particle path impulse shear in this movie made by Fossen. You can see all the lines move along curved path, only along this apophysis of this one, the particle moves in a straight way. So at the end, these two blue line are the apophysis. And the angle of the apophysis is 90 degrees in pure shear. This is simple shear, dextral simple shear. And the particle moves parallel to horizontal axis and does not change the position along the vertical axis. And you have only one apophysis. So alpha is equal to 0. And the situation is this. When you mix simple shear and pure shear, you have combined situation. All the particles move along curved lines, only along this this black line, the particle moving in a straight way. This is a stable apophysis that is parallel to the flow, parallel to the shear zone, and this is the unstable apophysis, the ones that rotate from 90 degrees to parallelism to the other one. So in this way, this angle is related to the amount of vorticity or the amount of pure shear and simple shear of the flow. Non-coaxial deformation is typical, of course, of a shear zone, but also between convergent plate, where the convergence is oblique with no uh, um, straight collision, but when they move obliquely each of the other, the plate. So the internal part, this internal part of the formation is characterized by both simple shear and pure shear. So there is a general flow. In this graph made by Riclot, you can see here the vorticity number from 0 pure shear, 1 simple shear. The 50% of pure simple shear is put at 0.71. That is, in this situation, you have the 50% of pure shear simple shear. In this part, you have the formation dominated by pure shear, and in this part, the formation dominated by simple shear. Simple shear is much more important. You can see the same in this much more simple graph. Start from pure shear, general shear, equal amount, and simple shear dominated. So just to have an idea. Okay, now we go a little bit inside the flow of the formation. I avoid the mathematical part because it's very boring, but you can find in the mm, in the paper by Cipolias, this one. Mm. So in one deformation, you have the instantaneous stretching axis. The instantaneous stretching axis are more or less the deformation that happens instantaneously. So you have the shortening axis, extension axis, and the axis, maybe X, Z, and Y. And in this case, the vorticity vector is parallel to this axis. Okay? So the physical meaning of vorticity also could be expressed in a mathematical way, but it is equal to the sum of the angular velocity of any pair of instantaneously orthogonal material line in the vorticity profile plane. So you should be perpendicular to the vorticity vector, and if you take in consideration the angular velocity of this line and this line, the mean value is more or less the vorticity of the flow. It is also twice the average angular velocity of all material lines lying in the vorticity profile plane, and it is twice the rate of rotation of a rigid spherical particle in clearly deformed matrix. So these are the definition of vorticity, but the amount of simple shear and pure shear is much more easy to remember. Okay, just we spoke about the monoclinic and triclinic deformation. The easiest way to deal with vorticity is to consider the vorticity axis, rotation axis, parallel to one of the deformation axis of the instantaneous ellipsoid, one of the ISA, usually the y-axis. And if this axis is oblique with respect to the ISA, we deal with clinic deformation. It is very difficult to find and also to deal with. But for very high strain, usually the vorticity is parallel to the intermediate axis of the finite strain and also of the instantaneous stretching axis. And this helps a lot to reveal the deformation. Okay, we can go ahead with this. Okay, we have to distinguish in between vorticity K and vorticity M and N are different point of view of the vorticity. This is instantaneous vorticity, this is finite vorticity. This is another kind of vorticity that we can consider when there is increasing volume of the rocks. But anyway, if you are in this condition, monoclinic flow, plane strain condition, no deformation along the y-axis, and the steady state deformation, that means deformation is constant through time, all these number, Wm, N, K, are the same. So we put in the more simple condition. Okay, so monoclinic flow, steady state deformation, and plane strain, no deformation along the intermediate axis of deformation. Let's just be correct. Uh, just a look to the vorticity, pure shear, vorticity equal to 0. 0, 1 vorticity is a general shear. Simple shear vorticity equal to 1. If vorticity large to 1, and from 1 to infinite, more or less the path are elliptical of the rocks. If vorticity is infinite, the particle is circular, and we have a rigid body rotation. So, but this is not only the only one flow that you can find. There are other strange kind of flow, but I avoid to put just not to confuse much. Okay, so in a flow, you have apophysis of the flow and the instantaneous stretching axis. The apophysis are the straight line followed by the particles when they move during the formation, and the instantaneous stretching axis are the direction where material is extended or shortened instantaneously at each instant of the formation. So, is when you deal with a flow in a shear zone, for example, in a transpressional shear zone with a simple shear and pure shear, you have the stable of apophysis, this one A2, that is stay parallel to the shear boundary, but I cannot see the apophysis in the rock, of course. And the other apophysis, A1, make an angle alpha with the stable apophysis. Okay, there's the apophysis of the flow. Then there are the instantaneous stretching axis, shortening, elongation, direction of deformation at each moment of the deformation. And then there are X, Z, and Y that are the three axes of the finite strain ellipsoid. Mm. So there are three kind of axes. The finite strain ellipsoid, so that the X, Y plane mark the foliation. It is the only one thing that I observe in the rock. In the rock, I see the foliation that is the trace of the X way foliation. It is a physical thing. The instantaneous stretching axis I cannot see. I cannot see only some structure related to this one. And also the flow apophysis are not easy to observe, of course, in the rock because you cannot see the displacement of the particle. So it is not easy to deal with this object. Uh, the vorticity is the cosine of the two apophyses. So if it is possible to see the apophysis in the rock, I can calculate the cosine of this angle and I have the vorticity, so much more problem, but it is not so simple. In this case, what is the difference between this and this one? What difference do you see? The angle alpha is changed and also the A the A2 apophysis is rotated in this position. So, and you can see also this arrow. So here you have shear and compression, so transpressional deformation. Here you have shear and enlargement, stretching. So there is a transtensional deformation. So it is exactly the same situation, but rotated of 90 degrees. So usually these angles are small and these angles are quite high. So this elongating shear zone parallel to the shear on the left, and this elongation is perpendicular to the shear. So sorry for this question, but it is a little bit important for the flow because when you have non-coaxial deformation and you can calculate the vorticity and you have a strain marker such as conglomerates or deformed cluster and so on, you can put all together this information, vorticity and strain, and by this apparently complicated equation, but it is not really complicated. You can put in this equation here the vorticity value, maybe 0.7, 0.7, 0.7, and here the axial ratio along the XZ section, maybe 4. You solve this um, equation and you find S. S is the shortening or the stretching along the shear zone. Of course, you have a positive stretching in vertical and a negative stretching in horizontal that is extension. So you can calculate how much material is extended due to vorticity and strain. You remember the cake effect like a toast with marmalade inside or jam inside. You shorten and the marmalade go away. In this way, you calculate exactly how much material could put in elongation along the shear zone. And this method has been used by the Don Kellett, Rick Lowe for the South Tibetan detachment, also in some paper, also in Argentera in the Variscan shear zone. Uh, It's useful because if you have these two values, you can combine and calculate the amount of extrusion, lateral extrusion. Okay, this graph is more or less vabbè, is more or less the same. You have shortening perpendicular to the flow plane in percentage and extension parallel to the transport direction. The red line is for no stretch along Y, that is plane strain. But if you have constriction, you have this kind of line, and flattening, you have this kind of line. But okay, you can use this equation with no problem. So after all these complex things, we can start to give a look to the method to calculate this vorticity analysis. This is nice, has been developed by Grasemann, an Austrian geologist, who worked a lot in this part of the Himalayas. And he found that in tension gases and stylolites, you can calculate the vorticity because you know that these veins are formed in this position, then rotate when the formation go ahead, so they are not more able to open in this direction, and the new fracture form according to the sigma 1. So the tension gases and also the stylolite. The stylolite, remember that the peak of the stylolite are more or less in the direction of sigma 1 or in the direction of the shortening. So Bernard Grassmann found that the initial angle of these tension gases is parallel to instantaneous stretching axis 1. So at each instant, you have direction of shortening, direction of extension, and these lines are parallel to the instantaneous stretching axis 1. So it is simple if you take consideration the angle between this initial line and the fall plane. For example, C is 8 degrees. The sin of 2 times um, epsilon, epsilon is 0.7. So the vorticity in this kind of object is 0.7. 0.7 means close to 50% of simple shear and simple shear. 50% is just 71, but 0.07 is close to maybe 49. This is very nice because in the field you observe very frequently tension gases, rotated tension gases. So if you have a lot of these, you can also calculate vorticity also in brittle ductile condition with no much more complex calculations. So keep in mind this possibility. If you are interested, there is this paper by Grassmann and a paper by Fossen and Tikoff, 1993, on the Journal of Structural Geology. Anyway, in this review by sorry, by Paris Xipolias, this method is reported and described. Okay, when we go in the ductile field, we sometimes we need to use the quartz C-axis fabric because uniaxial crystals such as core quartzite are very useful to characterize the formation. So, for example, here you have the C-axis of quartz as a main axis oriented in different ways, so an isotropic situation. after deformation, you have the slip along slip plane in the quartz. So the z-axis move, and of course, it doesn't go in the same orientation, but it show a pattern that is characteristics. For example, after deformation, simple shear deformation, you put in this way and in this way. So from this kind of a pattern, it is possible to calculate the sense of shear, but also the amount of vorticity of the flow. For example, when you make a lot of measurement of quartz, you can have a symmetric distribution. So all the points are put in this shape. You have a symmetric distribution, maybe pull shear, or an asymmetric distribution like this that is related to non-coaxial deformation component of simple shear. So it's uh, it's useful. Uh, it is called quartz vorticity gauge. You can have oblique grain shape fabric in quartz. You remember the ribbon quartz of the Milonite. If you take this orientation, you can gain information about several things. Also, the C prime type shear band are very useful because they are related to the instantaneous stretching axis. I go. Okay. I show you 2 days before how C prime works. If you have this stable apophysis in the flow, this unstable apophysis, the ones that rotate according to, and usually the maximum shear strain is bisector of this angle. This means that C prime shear band developed in this direction because there is a maximum shear strain. So it is very easy. You can take a measurement of this C prime with respect to the high strain foliation. You double this angle and you find the vorticity value, the cosine of 2 times 38 degrees, that is this angle. Of course, the problem is that sometimes this C prime shear band rotate, so you can see a lot of measurements here, and you can take some 10, 20 measurements. You take the highest angle because probably they are the ones that are formed parallel to the maximum shear strain before rotation. When they rotate, the angle is lesser and lesser, so you take the highest angle. This is another way, another very simple way to gain information of the simple shear in myelonitic rocks with C prime fabric. It is quite common. You can see also in the field in polished slab of rock. Okay, the limitation of the methods that we use is the assumption of monoclinic flow with vorticity vector parallel to the y-axis. This assumption should be checked. The way I check is to observe this section, this the vorticity plane, the XZ section, to observe here if there are rotations. If there are rotation, probably you are oblique to the vorticity axis. You are not in a monoclinic flow, so you have to do some very complex thing to left the sample or put the sample away. So this rotation, okay. In this section, you must not observe rotation if you are in monoclinic flow. Okay. Do you remember when I show you the shear zone? I show you the behavior of the object. Axial ratio increases with shear, and the angle decreases in intensity as strain increases. In this graph, you can see the strain ratio and the angle of the long axis of the strain ellipse. If vorticity change, you have different path of the angle, and you can in this kind of graph you can mix the axial ratio and the angle. You you obtain the axial ratio of the finite strain ellipsoid here, the angle in between the the long axis and the shear zone. You can put in this graph, for example, strain ratio is 10, the angle is 10 degrees. You are in this graph that is more or less vorticity close to 0.9. So high strain simple, high prevailing simple shear. Mm. Because these angles are different from the angle followed by the, the strain following, diciamo, deformation not characterized by non-coaxial deformation. So more or less the vorticity can be obtained by this equation, this angle, this axial ratio. You can use this equation or this graph if you have diciamo, a good idea of the shear zone boundary. Of course, if you are in a field in a colorimetric scale shear zone, this cannot be applied because you cannot see the shear zone boundary. You can observe the myelonitic foliation, but to the micro scale, it is not exactly parallel to the shear zone boundary. There is always an angle 1, 2 degrees. In shear zone where you can see the boundary very well, you can apply this method. Okay, if you cannot see the boundary of the shear zone, but you have object deformed, you have the macroscopic foliation, the magnetic foliation, the amount of deformation, so you have the ratio xz, you can gain the information uh, of the shear plane using the z-axis of quartz. So you have to put the thin section under the electronic microprobe with ABCD, backscattered electron. They can measurements of the axis. They project in a stereographic projection. You can find the skeleton, this kind of figure that is characterized by the quartz. So you are trying to define this kind of a skeleton uh, in the projection of a z-axis of quartz. And in the central part, you have to join these two maxima, and the perpendicular line to these two maxima is more or less the shear plane, because experimental works and natural observation found that this is a useful method to calculate the shear plane, because as shear goes on, the z-axis of the quartz are oriented perpendicular to the shear plane. So you can use the z-axis, the central part of this girdle, to obtain the perpendicular, so you have the shear strain. So you can measure the angle between the macroscopic foliation that you can plot the stereographic projection, and this yellow angle is a beta angle between the shear plane and the macroscopic foliation. So you can use the previous equation with no problem. So uh, you have to use z-axis of quartz. Okay. Ah, I'm going backward. Okay, if you have oblique grain shape fabric, such as the ones that we observed in the Mylonites of the Kumbu in the thin section, you have ribbon quartz with oblique foliation. you can use this oblique grain shape fabric because when you have an oblique foliation, the grain of quartz start to grow parallel to the instantaneous stretching axis, the extensional instantaneous stretching axis, then rotate into parallelism to the shear boundary, and then re- restart to recrystallize. But when they start to crystallize, they are parallel to the instantaneous stretching axis. So you can measure the long axis of this subgrain or oblique grain. You put in a histogram. You can, of course, use you needed to do several measurements. There are angles varying from 0 to 28 degrees. If you take the maximum angle, probably is the one that has been grown parallel to the instantaneous stretching axis. So you can use this this angle to find the this angle delta between x and the instantaneous stretching axis. Mm. Okay. So there are several variation of this method, but okay, take in mind that we can use quartz axis in different ways to characterize the vorticity. Another interesting, more simple method is the use of a rigid porphyroclast. You can see in this picture uh, transgression with left sense of movement, compression perpendicular to the foliation. You have a stable apophysis here, a rotating apophysis here with an angle alpha. And you can see that some porphyroclast rotate continuously, developing delta type tails. Some other rotate less and develop the sigma type tails or mantles. And you can see also the famous back rotated porphyroclast because they are rotating in this direction to the right, but they develop the tails according to the shear direction. So the tails are attached on the long side of the crystal. But in this way, I can use the distribution of porphyroclast to detect the amount of vorticity. We use this kind of graph. This is the angle of orientation of the long axis of the clast. On the horizontal line, you have the aspect ratio of the porphyroclast. It is just not the major axis divided minor axis, but it is the axial ratio elevated to 2 minus 1 divided r to 2 plus 1, just a little bit difference. But it is very nice because this is the equation that give you directly the vorticity. So more or less you put all your clast in this graph, means that you have this aspect ratio zero point 0.4, the orientation 6 degrees. So you have this dot, then this one, you plot every one. You can find two kind of distribution. The red one are classes that rotate continuously. If you give a look, they have a very low aspect ratio. They are rounded, more or less. In this part, the yellow clast are the clast with an higher aspect ratio, so they are more elongated and became more stable and parallelized to the shear plane. And these two distribution are separated by a line, by a cutoff point. You can check this cutoff point. If it is 0.6, this is directly the vorticity in this kind of graph. So 0.6 means that the deformation is made by prevailing pure shear. Some people uses also the tails. So the red one are more or less delta porphyroclast. The yellow one are sigma porphyroclast. Okay, if you have so much tails, you can use, but anyway, you can plot this also the axial ratio and the orientation without taking in consideration the sigma or delta porphyroclast. So you just put all the measurement, the graph, and try to find the distinction, the cutoff point in between the classes that rotate continuously and show orientation up to 90, minus 90, from the ones that are concentrated along the shear plane. And this line as a line of the flow, the theoretical line calculated for the flow of each aspect ratio. So you can have also a graph like this, much more simple. You can plot the orientation along axis and the axial ratio. So you put all the point here, and then you can try to find the cutoff line here. But usually there is not only one line, but a zone of uncertainty. So you can put a lower and an upper uh, cutoff line. So you have a range of vorticity, maybe 0.73, 0.78. Okay, but it is exactly the same. So for this method, you need to have a rock with a deformed porphyroclast, maybe some sigma tails and so on, but I don't take care of this. This is a myelonitic foliation. You can have the long axis, the short axis, and the orientation of the long axis with respect to the foliation. So you have the axial ratio and the orientation of each porphyroclast. These are just enough parameters to build up this graph. Okay, if you calculate the aspect ratio, that is beta. I don't remember. Ah, minus -1. And this is also the vorticity value. So we can use this kind of graph. Okay. So it is much more easy to plot on this kind of graph. So these are more or less an overview of the main methods to calculate vorticity. For the rigid porphyroclast method, there are some problems, some prerequisites that you need to know before apply this method. The matrix behaves as a Newtonian linear viscous fluid, so should be simple deformation, Newtonian, not with exponent, and we will not control this, we assume. The clast should be perfectly bonded to the matrix, so they're connected to a matrix and rotate, not disconnected or separated from the matrix. The class should be perfectly rigid, so means you have to rotate this one with not a internal deformation. So if you use the class for strain, means they are deformed, you cannot use for vorticity the same class. Okay, this is very important because some people make a lot of confusion with this. The metric strain should be high. The much higher strain has a much better results. And you have also enough population of a class with axial ratio larger than 3 and 4. Because if you have not enough class like this, you can see in this graph, okay, also in this one, you need to separate the continuously rotated cluster from the stable cluster But here you can have a large number of clusters, not only one or two, because should be very big error moving with this. So you should have a rounded cluster and elongated cluster with axial ratio 3, 4, 5. So you have two population, well-defined population that you can separate by the cutoff line in the graph. And there is also another problem because when you have uh, when you cut the section, you can cut the rocks in this way. So this cluster is cut in the central part, and you can see the maximum axial ratio. This one is cut just on the border, so you have a minimum axial ratio. So you have also some problem of the cutting effect. So Tycho Fossen established an error of the vorticity, more or less 0.1 error, the vorticity. So means that 0, 1 and 0, 2 are more or less the same. But in a paper with Jacopini and some colleagues, we calculated the cutting effect and the several other effects. And to be safe, to be sure, usually the error could be close to 0.02 maximum. So if you have vorticity 0.3 and 0.4, you cannot use to make some bigger reasoning because they are more or less the same number. So you cannot separate these, I mean, much more pure shear, much simple shear. They are the same. So they give an idea of the formation. So if the difference are zero point 0.3, zero point 0.4, zero point 0.5, okay. And due to this limitation, the best thing to do is to apply as many methods are possible on a given sample using high quality data. So don't use only C prime or Porphyrioclast. Try to use all what you have or what you can and compare the result. In this way, uh, you can build up a little bit better data. Okay, just some natural example from Greece. Uh, there are some paper by Xipolias worked on the strain I show you 2 days before, and also he calculated the vorticity approaching in a tectonic unit, approaching the thrust zone. In red, you have the axial ratio and beta method by quartz shear fabric axis. Uh, this oblique grain shape use the quartz C-axis fabric, and in yellow the axial ratio of strain and delta method. So with different method, this the rigid Porphyrioclast method, the blue used in the uh, Mount Everest or at the scale of origin. So you can see, for example, in this tectonic unit, you have simple shear predominating in the upper part, and pure shear dominated in the central part of the unit. On the unit, then simple shear increased at the thrust at the base, thrust at the base of this unit in Greece, and the same more or less happen in the Himalaya. This is quite old. There are much more data now, but you have something between a simple shear, pure shear in the central thrust, then pure shear increases in the central part of the Great Himalayan sequence. Then you have a very large amount of simple shear approaching the South Tibetan detachment using uh, different methods. This just data from Mount Everest area, a little bit similar to this, but not so much. This is the Raft River Mountains in USA. It is a tensional shear zone and the vorticity changing in a strange way going to the lower part. So you can use also at the regional scale. Of course, when you go through the grid Himalayan sequence, it's a problem because you have different metamorphic conditions, so the data are not so well comparable. And when you use C-axis fabric of quartz, you have to remember that the quartz could be very easily deformed, so it cannot record all the history of the formation, but only the latest stage. So these are the main limitation. So for this, I I stop you to fill with information and the strange formulas. Thanks. But if you like, there is an exercise, but I can show you simply what to do because uh, just you can estimate the strain. This sample, you know, is made by a rigid porphyroclast rotating during deformation. These rocks are characterized by pure shear, simple shear, and uh, of course, I have not the value for this one because I forgot in Italy. But this is an exercise from Paris Xipolias that put the short axis, long axis, and the angle of the porphyroclast, and just and he also build up Excel program, Excel file at this one. Okay. So I can put here the short axis, long axis, and the angle, and the program, Excel program, calculate the ratio and the step factor. So, for example, this is asymptote 68, angle 36, maybe the second 33, 46, 70. And if you give a look to this graph, is plotting the point on this graph. So someone wanted to put the number inside just to give the distribution. Some voluntary people. I give you money if you come here. No, just try what happened and how to decide the cutoff point. No one? Yes. Yeah, yeah. So, okay. 86, 101. Okay, go directly here. 35.